All right. So last time in class, we did Hess's law with system of equations. We did it with the lab. Now we're going to do a couple of practice just to reinforce. What slide it is. We'll do this one. We're going to do this one on the next slide. So this is from the, so 6.61. Okay, so we want to know what is the enthalpy of the reaction for this reaction. Sulfur rhombic going to sulfur monoclinic. The difference in the names is that sulfur occurs in different forms depending on the temperature and the crystalline structure. And those words are just basically saying what type of structure is it. This equation right here, we want to keep as is because that equation has the sulfur rhombic as a reactant, and that's what we have in our equation. This equation has the sulfur monoclinic as a reactant, but we need it as a product. So this reaction gets reversed, and all that means is we change the negative 296 to positive 296. Now, if we line those equations up, we would have sulfur rhombic plus O2 as a gas, producing sulfur dioxide as a gas. In the second equation, we would have sulfur dioxide as a gas, as a reactant, because we're reversing it, and we would have our sulfur monoclinic as a product, and we would have our oxygen gas as a product. Questions so far? That would allow the sulfur dioxides and the oxygens to cancel out, leaving us with just these two. And we basically then just take what is the value for the enthalpy of the reaction, 296.06, and the second reaction is positive 296.36. So we basically just add these two equations. Once we cancel that out, add to the sulfur rhombic, giving us a sulfur monoclinic, which is what we want. And our enthalpy for that reaction is simply going to be the result of adding these two together, which should be positive 0.30 kilojoules per mole. Who's got questions? Okay. A little simpler than the reactions we had last time, right? But the basics are still the same. Do another one. I'm going to let you guys lead through this time around. Let's see here. Which I'll call randomly. Diamonds. Nope, nobody has that. That's in the very back row. Jack of clubs. Who's got jack of clubs? Look at your tables. Look, call them out. I got a bunch of them that don't have them. Five of spades. Everybody know what a spade is? I mean, I've had every class. I've had at least one person say, "What's that?" 7 of spades. Five of diamonds. All right. So, I'm going to start us off, and then you're going to pick up where I leave off.
Okay.
We want this equation, okay? That's what we want. This equation, we're going to keep going the same direction. But Anya, what do we need to do to that equation to make it useful here? So we would have 2 graphites plus oxygen gas producing carbon dioxide gas, or 2 of those, 2 carbon dioxide gas. So basically by multiplying by 2, we're doubling everything in that reaction. Nine of clubs. Eight of hearts.
Okay.
So what's next? And it doesn't matter what goes next. It's whatever you choose. It's what you see most easily.
H2, the water one, well, not mixed water.
This one?
Yeah.
What are we going to do to it?
You want to multiply it by 3?
Multiply by 3. Do we need to do anything else to it?
We also need to multiply that.
Why?
So that the hydrogen gas and the oxygen gas are on the opposite sides of the current hydrogen-oxygen gas.
Why would you want that?
That's allowed to do.
So here's the thing. We have in this equation, the equation we want, we have hydrogen gas as a reactant, right? And you said correctly, we want to multiply this reaction by 3. That'll give us our 3 hydrogens. But if we flip it, where does that put the hydrogen now? As a reactant or a product? But we want it as a what? We want it as a reactant. So we're not trying to cancel this hydrogen out. We're trying to get everything to add up to leave that hydrogen there. Does that make sense? That's why we had to so we want carbon graphite. This equation we kept as is in the direction, same direction. But we just multiplied it by 2. Because we need to have graphite as a reactant. We need to have hydrogen gas as a reactant. This is the only equation that has hydrogen gas as anywhere in it. It's also a reactant though. So we want this equation to go the same direction as it's pointing right now. Just multiplied by 3. That make more sense?
Yeah.
So we've got 3 hydrogen gas plus 3 halves oxygen gas. And I know it looks weird to have fractions in our balanced equations. That's what we have to do, okay? Now, I don't care, I don't have a preference. This is up to you. 3 halves, or you can make it 1.5, either one. I leave it up to you. Produces 3 water. Is everybody okay? Oh, lucky you, Allison. 9 of hearts. Huh?
I have 7 parts.
Of 7? Most previous. No. 9 of hearts. Who's got 9 of hearts? Nobody? Ten diamonds. Queen of clubs. There's queen of clubs. So, cool. What do we need to do to this reaction? We're trying to make this one. Your focus is going to be this. So we've already taken care of those two. What do we need to adjust in that equation? You need to ask a question. Ask a question.
So I was wondering,
What is in the final equation we want? That's this. That's in that equation.
2C graphite.
And what's in this equation here? That's in the equation that you're dealing with.
So there's carbon. So carbon. So hydrogen. So 6 hydrogen. 2 carbon.
This has already been taken care of by reaction one. This first reaction. I'm gonna number them. 1, 2, 3. This has already been taken care of by reaction 2.
So we're focusing on the 2C to 8-6, right?
Yep.
Divided by 2.
Divided by 2? Why?
They're trying to get rid of a 2 in front of it.
Okay.
Because that's turning 4 and 12. 4 carbon and 12 hydrogen.
So that takes care of this 2 and reduces it down to 1 like we want to have here. Is there anything else that we need to do to this equation?
Divide 1/2 with the minus 3,119.6 kg. kJ slash mole.
Right, okay, so that follows. Is there anything else that we need to do besides just multiply by half?
write it down there.
So cool, what's the problem with what you've got there now? If we add those those three equations up in systems of equations, what's the problem? It's glaring.
This is the name of the calculation or addition.
Where's the C2H6 in the equation we want?
In the bottommost equation.
That's not the equation we want. The equation we want is the one that's calculate enthalpy for the change for the reaction. This one right here. This is the equation we want.
Oh, so that's, okay. What it's saying is 2C graphite plus 3H2 is equal to C2H6.
Yep.
But our C2H6 is on the product side.
The one we want, correct? And where did you say to put it?
Reactive side.
So what do we need to do to that reaction? Besides just multiply it by 1/2.
Move it to the other side.
Say again?
Move it to the other side.
So just put this over there.
But there's a catch. I don't think it's that easy.
No, it's not, because that makes no sense. What do you have to do to the equation? You can't just simply say, move this to the other side. If you moved it to the other side, your equation would be 7O2, or 3/2 O2, 7/2 O2, producing 2 CO2, 3 H2Os, and a C2H6. That makes no sense. That equation is no longer balanced.
You have to balance it again.
You can't.
Yeah.
Class, what do we gotta do? Somebody
Flip it.
flip it, reverse the reaction. If we do that, what do we need to do? We gotta make this positive instead of negative. So reverse the reaction, you get 2 CO2 plus 3 H2O, producing C2H6 and 7/2 O2. I'm not gonna put the states in there because everything cancels out properly. And now we cancel out. So we're gonna try to cancel out. This stays. It can't, there's nothing to cancel out with. Hydrogens, they stay. There's nothing to cancel out with. how many oxygens do I have on the reactant side in total? I get 7 halves. Because you can look at this as 4 halves, right? The other way you could do it is if you had this as 1.5, then you have 2 plus 1.5 is 3.5, 7 halves. So both of these oxygens are going to cancel out that 7 halves oxygen. 2 CO2s cancel out. 3 H2Os cancel out. So we are left on the reactant side only with these, and on the product side with that. We then use this, make sure you multiply that by 2. This we're going to multiply by 3. But both of those stay in the same direction because we didn't need to reverse them. This one, make it positive, multiply by 1/2, add them all together. Everybody do that. Unless you've already got it done. Anand, you already have it done?
Yeah.
What do you got?
84.6 kilojoules per mole.
Positive or negative?
Negative.
That's important, okay? So if we carried out this reaction, if I took graphite and I put it into a hydrogen atmosphere, and we cause that reaction to take place, technically you could. It's not going to be an easiest reaction to cause it to take place, but you could burn the graphite in hydrogen gas. Get this. Is that reaction going to be exo or endothermic? Why? It's releasing energy because of the negative sign. Okay. Questions? That's flavor 1 of Hess's law. Using the method or a system of equations. That's flavor number 1. Okay. Flavor number 2. A little bit different. Requires me to go back to this. So, the enthalpy change for a reaction carried out in a series of steps is equal to the sum of the enthalpy changes for the individual steps. So I guess you say, this is the system of equations. The delta H, degree sign F, okay, that has a name. It's called the enthalpy of formation. I want to write some of this down now because this is not up here. I need to give you a definition for the enthalpy of formation if you haven't picked that up from the owls or reading. The enthalpy of formation is the formation of the enthalpy of formation is the energy change when 1 mole of product is produced from the elements in their standard state. Say it again. The enthalpy of formation is the energy change that occurs when 1 mole is produced from elements in their standard state. I'm going to just stick with what I used last period because I know that there are values we can look up. Now, I will ask you to write out an enthalpy of formation. They're easy. Just make sure you know the definition for it and follow that definition to a T. If I ask you to write out what's the reaction for the enthalpy of formation for phosphoric acid, actually just hydrogen phosphate. It's an acid only when it's in water. This is not in water. I'm going to put down here what would that reaction be? What does the H3PO4 have to be? Look at the definition. What's that?
The standard state.
Yeah, but what's at the standard state? What's that? The elements. What is the H3PO4 in this? Somebody read me back your definition.
The energy change that occurs when 1 mole of product is produced by elements in their standard state.
What?
So what is the H3PO4? It's the product. And how much do we need to produce? 1 mole. So its coefficient can only be 1. What elements is it made of?
Hydrogen, phosphorus, oxygen.
Hydrogen, phosphorus, and oxygen. Okay. Four diamonds. So, what do we have to put as our reactants? Do you know what hydrogen is in its standard state?
Yes.
Correct. You know its formula.
H2.
Good job. How many of those are we going to need, though?
And we have
You're on a roll. Keep going.
phosphorus, solid,
Correct.
and then O2 gas. 2 of those.
That's it. All you got to do is break it down, put the elements in their standard state. Watch out for your diatomics. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. I'd include acetylene, but you'll never see acetylene in any reaction. There's not enough acetylene on Earth. There might be like 100 atoms on Earth at any one point in time. Don't worry about it. Okay. That's it. That's the enthalpy of formation. That's the reaction for it. The actual numerical value is something you could go look up. We will do that here in a second. Okay. Somebody's doing. Three hearts. So those ones over there, Sophia. Those the three and four. No, that's the key.
You almost called on me again because I played a 3 of diamonds.
7 clubs. What is it?
2 iron solid, and 3 or 1.5 O2 gas.
It's good to me. Or you can do
Gas.
3 halves.
He said yes.
Gas. Thanks. Questions? People, it really is that simple. Okay? So if you're asked, what's the enthalpy of formation, or if you guys ran into the owls, those of you who had completed them, it asks for the enthalpy of formation from the elements. And you just wrote out the reaction, you just had the coefficients to make sure they add up properly for 1 mole of your product. You guys remember seeing that, right? Okay, now you know what it is. Now, let's see how they're used. So in Drive, you have a document. Switch over here. It's in the reference for the class resources. Now, in the class resources, you have bond enthalpies, which we are using in this chapter, in this unit, and you have the thermodynamic data, AL data. So these 2 documents they're the AL data that you have when you go to the resources. So instead of going to that drop down, you can open this up in Drive and do a split screen or something along those lines if you wanted to, okay? And like I said, this is the AL data. All I did is just simply printed out the data. We will only be using this first column of data. The Gibbs free energy and entropy, we will be using second semester. Okay. All of the data is given in kilojoules per mole for your enthalpies of formation. So if we scroll down here, like for the phosphoric acid, that's going to be a phosphorus compound. So if we look at the phosphorus, we will see that we have H3PO4 liquid and H3PO4 aqueous. You do need to make sure you pay attention to the states. Make sure you're using the correct values. So because that was as a liquid, we would be looking at this. So that's going to be negative 1279. So if I had hydrogen in its pure form, its standard form. I had phosphorus in its standard form. I had oxygen in its standard form. And I caused them to react to make the phosphoric acid, or the H3PO4. This is how much energy would be released in the formation of that compound. I will tell you this right now. If you want to make H3PO4, you are not doing that reaction. But if you do make H3PO4, no matter how you do it, that's the amount of energy that will be produced. Okay? This goes back to that Hess's law. It doesn't matter how you do the reaction. All that matters is what you start with and what you end with. Right? If I had this many moles of iron and this many moles of oxygen, yeah, we could do this one. Go and look up iron compounds. The iron compounds. Go. Hey, what? Questions? Now, we use that data that we just looked at with this equation. do not be intimidated by this equation. It looks much scarier than what it really is, okay? So we're going to do this problem. We want to know what is the enthalpy of the reaction. Quick note, delta H, we sign the F. If you ever see that, it's a formation. If it's not a formation, it won't be there. Okay? For example, is that an enthalpy of formation? No. The only criteria it has is you have a product. It is coming from its elements, and they're in their standard state, but what's not making the criteria? Has to be 1 mole. These are not enthalpies of formation. Okay? Now, let's say that, pretend for an instant, that this was the number for that reaction as given. I'm going to erase the F. Could we get the enthalpy of formation from that information? Yeah, just divide everything by 2, right? Okay. The degree sign, this means standard. °C has to be that temperature, that standard temperature. 1 atmosphere of pressure if you're dealing with gases. One molar or 1 moles per liter if you're dealing with solutions. Okay. Go to the table. What is the value for calcium carbonate?
There's 6 of clubs.
There's queen of spades. You're gonna be, your job is table reader. .9? Okay. Calcium oxide. 600 what? 35.1. A carbon dioxide. That's going to be in the carbon section.
-393.
0.5? Okay. So, we're going to use this equation. This equation, what's this mean? Sum of the enthalpies of formation, which we just looked up, of our products minus the sum of our enthalpies of formation for our reactants. That's all it is. We're doing some addition, subtraction, multiplication as needed. Multiplication? Yes. If this had a coefficient of 2 in front of it, what would we be doing to this value? Multiplying it by 2. Okay? Now, so our enthalpy for the reaction, which will be ending up as a standard. If you get it, if you use standard enthalpies of formation, you're going to get a standard enthalpy. products minus reactants. So negative 635.1 plus negative 393.5. Now the reason why I am putting them in all the brackets and parentheses is because if this did have 2, we'd be multiplying by 2 in there, right? Now all of this right now that I have written is for my products. Products minus our reactants. Calculate it. Everybody, 'cause I'm calling on somebody. Moxie, you guys done this with organic?
Not yet.
Okay.
We just finished our like first week of like hybridization and whatever it's called.
I think you guys are coming up then on this where you're gonna make diesel.
At some point soon, yeah.
Ace of spades,
No, that's me.
not you. Ace of diamonds.
Hey.
We got
178.3 kilojoules per mole.
and that's positive, right?
Yep.
Now you don't have to put it, I like putting it just to, so there's no ambiguity there, okay? That means this reaction is what? Endothermic, because energy's gonna flow into that as part of the process. Questions? This is flavor 2 of Hess's law. Flavor 1 was using system of equations. Flavor 2 is using the equation for Hess's law. Okay, so for part A, let's focus on part A. For the following reaction, hydrogen chloride gas, when placed into water, turns into hydrogen ions and chloride ions. Resulting, so the enthalpy of that reaction, so this is saying the enthalpy of this reaction is negative 74.9. This question is asking, what's the enthalpy of formation for chloride ions? So this is our question. If I write out the equation, say, what do we have in this equation? What do we know in this equation? You know the reactant? What's on in black on the white background right now that we know in that equation? Ananya? Okay, so we know part of this, right? So we know the hydrogen part for that. What else do we know? Moxie?
The enthalpy change.
We know this. So if we go to plug into this, so if we go to plug in and start writing out this equation, we say we got negative 74.9. equals sum of H plus and chloride, hydrogen ions and chloride ions. What's hydrogen ions? Enthalpy of formation.
Zero.
Why?
So,
Can somebody tell me, please say, because they tell us that.
Some, tell us that.
Oh, this doesn't bode well for a test that you're gonna have to actually read the questions on. Holy cow. Holy cow. Zero. Why?
Because
it
that's
says
the
so.
thing.
Because it says so. Plus what?
Enthalpy formation of chloride.
The enthalpy of formation for chloride, which we don't know, right? It's what we're finding. What are we gonna write?
Some kind of
Variable.
Some kind of variable. What's Matt's favorite variable? Okay. I don't care what letter you use, just use something there, okay? That takes care of our products, right? No. Minus, now what are we gonna have to do? Because you're designated table reader. It is a gas.
Negative.
Hey, class, that's a good question, because in that table, you've got both aqueous and gas, right?
Yes.
Make sure you're reading the right one.
Negative 92.
What? Now, that's the only reactant, right? Close them up. X equals. Everybody, get out calculator and do it. Who's 6 spades? Anybody? 8 spades? Jack hearts?
Honestly, I like this system, but it won't work for a small class like this.
I know, but I'm okay with it. 2 hearts. Might have to give you guys extras. 7 diamonds.
I might be 7, I might be 8, it has both, I mean, I'm 15.
You're gonna do both.
Oh, am I both? Yeah.
Yes.
And then you got that.
What's your answer?
Negative 167.2.
Agree or disagree, class?
Yeah.
Okay. Alright, we're gonna do the next one.
That's kilojoules per mole.
It's kilojoules per mole. Alright. Given that enthalpy of formation of hydroxide ions is negative 229.6 kilojoules per mole, calculate the enthalpy of neutralization when 1 mole of strong monoprotic acid, such as hydrochloric acid, is titrated by 1 mole of strong base, such as potassium hydroxide. Now, this will become more, it'll become clear when we do acids and bases second semester. But this equation here, you have two options. You can write out the reaction as hydrochloric acid plus potassium hydroxide is going to give you what? Oh, come on.
Potassium chloride.
Potassium chloride and water. Okay? But this kind of gives us a hint. They're giving us the enthalpy of formation for the ion. This is a question where doing the net ionic equation is easier than doing the full out equation. Can somebody tell me what the net ionic equation for any strong acid with strong base, I remember you had an Al on those, is going to be?
H plus H plus.
That's it. Now they want to know what is the enthalpy of the reaction, right? What is the enthalpy of formation for hydrogen ions?
Zero.
Why?
Six.
Because they tell us that. What is the enthalpy of formation for the hydroxide ion?
Negative 2, 2, 7, 2, 6.
Why? Because they tell us that. Here, your table. And this is going to be liquid. Liquid. I will set up the equation. 5 hearts. 7 hearts. Set up the equation. I'll start you off like that.
Then we have negative 285.8. Minus 0 plus negative 229.6.
Everybody calculate, go. So these are the ones that know on for period 2. Go around and figure, so that's that back row. Yeah, get this one and that one. Six diamonds.
I got negative 56.2 kilojoules per mole.
Good job. Now.
Yay.
What was the enthalpy of reaction you guys calculated last time in class based on your lab data for the acid and base? Now that was for the salt. The 30-something was for the salt.
Negative 50 H 1.
-57.
Negative 58, negative 57. Class. This value right here is what it should have been close to. Because what did you mix? You mixed nitric acid, which is a strong acid, with potassium hydroxide, which is a,
Strong base.
and I just did the net ionic equation, right? The net ionic equation for any strong acid, strong base just does not matter. The net ionic equation for any strong acid, strong base is going to be the same. So there would be variation with this. That variation is going to be caused by the other things that are involved in there. So like this reaction of hydrochloric acid with potassium hydroxide is probably going to be a little bit different, probably in the hundredths or in the tenth place there, than what you guys measured. But they should, all acids and bases that are strong should be about the same. Okay? Questions? Is he gonna pay you to leave him off?
I mean, if he gives me $10, maybe.
Just $10?
You sell out.
You're cheap.
Yeah. It's not that hard to just write it down.
Questions? That's flavor 2. Not hard, right? Ananya, what's your question?
I don't have questions.
Oh, I thought you. All right, flavor 3.
Oh.
So many flavors.
You get to choose which one's your favorite. Actually, you don't. You get to choose which flavor to use based on what information you're given.
We have no choice.
So you have no choice. You're going to be force-fed whatever piece, whatever flavor it is.
All of them are bitter.
Just some less than others?
Yeah.
Okay. Annie, you ready? Okay. All right. So this is one of those things, it's just, it's easier to see than to try to explain. I mean, I got the notes up here. The only thing I will say is that this is essentially saying if we have a hydrogen molecule that's singly, so we've got 2 hydrogen atoms singly bonded to each other. To be able to do that, so this equation is basically saying we're breaking that bond. And this is the amount of energy required to break that bond. That by definition then would be the bond enthalpy. So the bond enthalpies are always being given as positive values because they're the energy that's required to break a bond. And I think I've mentioned this before, but I'll reinforce it now. Anytime you are breaking a bond, anytime you are breaking or weakening an attraction, that is going to be endothermic. Energy has to go in to do those things. Anytime a bond is formed, anytime an attraction is formed, that is going to be exothermic and will have a negative value associated with it. Okay? Now, what's different about my delta H?
Not standard.
It's not standard. These bond entities are not done at standard conditions. Okay? Now, having said that, that doesn't mean that the calculations are invalid. It just means that you would get slightly different values if you were doing it based on the standard enthalpies versus bond enthalpies. They're still good approximations, okay? So, we could go through and calculate the enthalpy for this reaction using bond enthalpies. The thing is, we gotta know about the bonds. And what tells us about bonds?
Table.
Yeah, but before we can even read the table, what tells us about bonds? We haven't done them for a while. You were asking one, I think you had, the pre-lab asked about. Lewis structures, right? Now, for the test, I will not expect you to write out Lewis structures. I'll give you the Lewis structures you need to use. We'll worry about that later on in the year, okay? Okay, so these are the Lewis structures for the things that are involved. Now, think of this as kind of like accounting. You just got to account for everything. Adding. Hydrogen-carbon bond. How much is it worth? You're going to have to go to a different, back to drive. And then go to the bond enthalpies. It should be up near the top. Yep, single bond. 413. Now, that's 413 kilojoules per mole of those bonds. How many moles of those bonds are we breaking in this? 4. So we would need to multiply this value by 4. Now I'm going to put a positive sign on this because in the enthalpy tables, they don't give you a sign, but I just got done defining bond enthalpies as the energy required to break a bond. So they would have positive values. Here's how this is working. Remember Hess's law. It doesn't matter what you do. It's what you start with, what you end with. How you go from reactants to products, it doesn't matter. Basically what we're saying is we're going to take apart, we're going to break apart everything, and then we're going to let them come back together on the product side in a different way. So what this is saying is we're going to add 413 kilojoules per mole of each one of these carbon-hydrogen bonds. So we're going to multiply it by 4 because we're breaking 4 of them. What's the oxygen-oxygen double bond?
400.
How many of those are getting broken here? 2. Now there's only 1 in there, but we have 2 oxygen molecules. Now I'm showing you right now one version of this, which is, this is probably the most basic fundamental way of doing it. Now, by adding in these energies, whatever they add up to be, that would allow us to break all of these things, all the carbons and hydrogens and oxygens into separate atoms of those elements. And now we can bring them back together in a new way. What's the carbon-oxygen double bond worth? 732. How many of them are there? Just 2. Now, I'm going to put a negative sign on this. Does everybody understand why? Because what I say earlier, when you form bonds or attractions, it's what? Exothermic. Hydrogen and oxygen bond, what's it worth? I'm gonna put a negative sign on that because we're gonna be forming these hydrogen-oxygen bonds. How many hydrogen-oxygen bonds are we going to be forming? 4, because we have, in a water molecule, we've got 2 of them, but we have 2 water molecules. Add them up. Multiply them up. Add them up. Four hearts. Who's 4 hearts? Somebody's 4 hearts. Who's 4 hearts? No, somebody's got to have it. Huh? 4 hearts? Isabel, what's Zoe's?
She's 3 and 4 hearts.
Text her, tell her I want the answer right now. 2 diamonds.
Sweet. Negative 668 kilojoules per mole.
Agree or disagree?
Agree.
Okay. Any questions on that? Now, we're gonna do the same thing, different way. What? I will let you choose on this one, Alston.
Alright.
Okay?
It's still better.
You can be bitter all you want, I don't care. I'm gonna leave the numbers up here, except I'm gonna get rid of the pluses and minuses, because this one, we don't have to worry about the pluses and minuses. We use the numbers as is from the table, okay? So, this one's weird. This is the oddball equation of all the equations you're going to have, because it's the only equation where we do reactants minus products. Okay.
Earth products.
Perfect. Okay. That's going to bother me now. You have no idea how many years this has been with that slide, and nobody has pointed it out. Thank you very much.
And they didn't point it out.
What's that?
I said there's no way that no one sees that. I said, well, they didn't point it out.
Yeah, they didn't point it out.
Yeah.
And I'm mad at all my former students.
How
Is that
many years
better?
has that been up there?
Probably 2.
2. Not including this.
Because I think it was either last year or the year before. Probably, I think it was 2. I started using latex as a way of writing, it's a way of typing out equations.
Yeah.
So it's just not, so it's just basically the weird italic font that equations have.
No, it's also the subscripts, the sums, all the different special symbols and stuff like that. Who's in calculus? All the weird equations that you guys write out, LaTeX, there's a way you can write all of those out in text for computers to read. Okay, so here's how this works. We basically take these numbers and we plug it into that equation and say, okay, we want the sum of, so our enthalpy of the reaction is going to be the sum of our reactants. So we're going to take 413 times 4 plus 498 times 2. And that takes care of our reactants. Now the reason why this works with this equation is because we want these to be positive. Because they're representing breaking the attractions. Minus 732 times 2 plus 463 times 4. Now these are the numbers that would be read straight off the table. They're positive values, but this corrects them. We want them to be negative. These are representing forming attractions, which would be releasing energy. That's what that does. Now just plug and chug, and you should get the exact same answer you got before, which was what? 600, what is it?
Negative 668.
How much?
668.
6.2?
No, just.
Or just 668, that's right. Kilojoules per mole. Also, that's the second way. Okay? So you could just set it up, line stuff up, and make sure you keep track of everything, and change the sign on what needs to be changed, or you can plug straight into that equation.
Are you gonna ever tell us to like we have to do it this way or the other way, or are we gonna go for it?
Well, it kind of depends on the data I give.
Yeah, that's true.
Because if I give you a data table that has only bond enthalpies, you're stuck with that. If I give you a table that has only enthalpies of formation, you're stuck with that. If I give you a set of once you see a set of equations given, you know what the hell you're doing. You have to arrange them and get the final equation, right? And so you kind of know what you have to do with what you're presented with. Now, can I mix and match? Can one part of the problem could you do with bond enthalpies and another part have to do, use an answer there to find out what the enthalpy of formation is? Sure. But the individual problem related to that is going to be based on what is it you have. Questions?
What's the test like format? Is it all multiple choice?
You're going to have probably about somewhere around 15 multiple choice. It's not a big unit. Well, probably maybe closer to 20 because we get the gases in there too. So I've got multiple choice questions. So it's not just the thermo stuff, it's also the gases. And then you're going to have, see, I got to watch time. Not for you guys, but for my period 2 class, because they're going to be cut short by about what, 5 or 10 minutes? I think it's 5 minutes. So somewhere between 15 and 20 questions, multiple choice, and then probably around 3-4 questions that are free response. They'll have parts like what you've seen in the practice. You got this question, you use that answer. You may use the answer in part A to do part B. and C and D may be a different set of questions, or maybe just a follow-up question to those things. It'll be made so that you should be able to finish in the time limit. Okay? I will cut you off on the multiple choice. On the multiple choice portion of the AP exam, you get your 60 questions for 90 minutes, so that's a minute and a half a question. So when I do it, if I had 10 questions, you're gonna have, yeah, 15 minutes. Maybe 20, you get a little bit of buffer there. Okay? And then the rest of the time, you can do free response. Does that answer it sufficiently? Other questions?
That won't hurt you.